Good afternoon, everyone. I'm Qingguo from Dr. Jeremy Levy's group, University of Pittsburgh. My topic today is Coulomb drag between graphene and lanthanum aluminum strongly tightened heterostructures. Coulomb drag is a direct way to study interactions between charge carriers. Drag experiment involves two closely separated but electrically isolated conductors. In such a system, an electric current flowing through one layer, which is called the drive layer, will introduce some voltage in the other layer, which is called drag layer. By this method, one can understand the scattering between charge carriers belonging to different layers due to long-range interactions. These scattering events are usually accompanied by momentum and energy transfer. A lot of pioneer work has been done in aluminum gallium arsenide double quantum well. As an example, in 2012, the perfect Coulomb drag is observed in aluminum gallium arsenide double quantum well due to the existence of exciton condensates. Recently, more and more experiments are done in the double-layer graphene system, since graphene can allow one to tune the carrier density in a wide range and has less disordered strength. Energy transfer mechanism and exciton condensates are found in graphene system. Besides, Coulomb drag is also performed in hybrid system, for example, in graphene gallium arsenide heterostructure. Due to the strong interlayer correlation, the ordinary quadratic temperature dependence expected in a weakly correlated Fermi liquid doesn't apply here. The lanthanum aluminum strongly tightened interface is a very rich 2D system that contains almost all the major electrical tuning properties in solid states, such as superconductivity, ferromagnetism, ferroelectricity, spin-orbit coupling, and so on. The interface exhibits unusual magnetic and superconducting behavior arising from electron-electron interactions whose physical origin is not well understood. Therefore, Coulomb drag can work as an efficient tool to study the electron-electron interaction. So here let me give a brief introduction to the lanthanum aluminum strongly tightened system. The lanthanum aluminum strongly tightened, which we call them shortly for LAO-STO, are both band insulators. But when we put these two materials together, there is a lot of interesting property will show up. For example, a quasi two-dimensional electron gas can be formed at the interface, especially when the thickness of LAO is above 4 unit cell, and this 2D electron gas can be tuned by applying backgate. With the conductive VFM lithography technique invented by our group, we are even able to write nanostructures at LAO-STO interface. So here is an animation showing how the writing and erasing process works. First, we apply positive voltage to the tip and then write two triangular shaped patterns, which we call them virtual electrodes. Those will help to form robust electric contact to the oxide interface. And then we apply positive voltage to draw one nanowire that connecting these two virtual electrodes. Then we will see a conductance jump between these two electrodes. After that, we apply negative voltage to the tip and create an insulating gap in between. So this will cut the wire. So this writing and erasing process is reversible in our system. So our goal is to integrate these two novel systems together. In our group, we grow the CVD grown graphene by ourselves and then transfer it onto the LAO-STO substrate. Instead of using the traditional PMMA, here we came up with a replacement which is called HiFLON to replace the PMMA. It will leave fewer residue on top of LAO-STO and supposedly have better transport property than the PMMA transferred graphene. So Here is the side view of our device. We put graphene directly on top of LUSTO. The LU can work as a barrier. And then we use the photolithography to pattern the graphene into a Hall-bar structure and make gold contacts to both graphene and interface electrodes. Here is the AFM image and the room temperature STM, which shows that even in atomic scale, our graphene is still clean. And at 2 Kelvin, we can see this quantized conductance of the graphene. The mobility is also relatively high. So here comes the question: is the LUSTO interface still writable with AFM tip, uh, even with graphene on top of it? Fortunately, the answer is yes. So here we apply positive voltage to the tip and then wrote two funnels to connect these two electrodes, and we also draw one nanowire that go across the graphene region. After the writing, we see a conductance jump between these two electrodes. A typical way to verify the nanostructures we wrote is to do piezoelectric force microscopy. And after we do the microscopy, we saw that there is one nanowire is at exactly the same location as we designed. With this powerful tool, we are able to perform the Coulomb drag experiment on our hybrided system. So here is a top view of our device. We first pattern the graphene into a Hall-bar structure, and then use the apply positive voltage to the AFM tip and create conducting channels underneath the graphene. We run a current in the graphene and measure the drag voltage between two LUSTO leads. At 6 Kelvin, we can see that the drag voltage measured in the LUSTO has a linear relationship with the driving current in graphene. And here is the temperature dependence of the drag resistance. We also measure the drag signal in the LUSTO as a function of the magnetic field and the voltage applied on the graphene leads. So here we apply voltage on both ends of the graphene leads and then subtract these two to get a delta V. So we plot the drag resistance as a function of B and delta V. There are two main features of this LUSTO drag signal. One is the superconductivity feature of LUO. So for STO is intrinsic superconductor. Besides, in the vicinity of the drag point, the drag resistance is giant. This giant drag resistance is also reported in other systems such as double-layer graphene system due to the asymmetry of electrons and holes at low magnetic field. Here we swap this drive and drag layer to measure the drag voltage in graphene. So we're running the current in the LUSTO and then apply a gate to the graphene at the same time to make sure the LUSTO is conducting. And we measure the drag voltage in the graphene. So this drag voltage shows different features at low and high magnetic field. So here is the result of one device, and we have another device. So here we have the full map of both low magnetic field and high magnetic field. And if we zoom in into a small magnetic field and high magnetic field, they have completely different features. And then we measure the drag voltage in graphene in two directions. One is the longitudinal drag and the other is the Hall drag. So in the longitudinal drag, the drag voltage is measured parallel to the driving current. So here the main feature is in low magnetic field in this longitudinal direction. And in the Hall drag, the drag voltage is measured perpendicular to the direction of the running current. So in this configuration, the main feature is not at low magnetic field, but instead it shows up at high magnetic field. It has this kind of stripe-like features. Indeed, given the presence of the two noncollinear current in the model, it's not surprising to see the non-zero Hall drag. So for short summary, we grown high quality CVT graphene and then transfer to LLSTO, and we can create nanostructures by using conductive FM lithography technique. We observe the drag resistance in both LLSTO and graphene, and drag signal in graphene have different features in longitudinal and Hall directions. Thank you.